Article 647 of the National Electrical Code, NEC, applies to the installation of isolated ground receptacles, IGAs, in commercial and industrial occupancies specifically for the protection of sensitive electronic equipment. Sensitive electronic equipment is defined in the NEC as equipment that is susceptible to damage or malfunction due to electrical noise or voltage transients. Examples include computers and data processing systems, medical equipment, telecommunication equipment, and audio or video equipment. According to the NEC, Article 647 applies when IGR are installed in commercial buildings such as office buildings, medical facilities, and computer data centers. Article 647 also applies when IGR are installed in industrial buildings such as factories, manufacturing facilities, and laboratories. Even if not in a commercial or industrial occupancy, IGR may be required where sensitive electronic equipment is present, such as computer workstations, server rooms, and medical examination rooms. Article 647 specifies the following requirements for the installation of IGR. Firstly, a dedicated circuit with no other loads. Secondly, 12 American wire gauge or larger copper conductors. Thirdly, an isolated ground system. Fourthly, IGR must be identified and labeled as such, and fifthly, equipment connected to IGR must be properly grounded. Article 647 does not directly apply in a residential location when installing an isolated ground receptacle for computer equipment. However, the concept of providing an isolated ground for sensitive electronic equipment is still valid. You should consider the following recommendations. Firstly, use a dedicated circuit with 12 American wire gauge or larger copper conductors. Secondly, install a grounding rod near the panel and connect the isolated ground to it. Thirdly, label the outlet as isolated ground for sensitive electronic equipment to prevent accidental connection of non-sensitive loads. An isolated ground receptacle is designed to minimize electrical noise and interference, thereby protecting sensitive electronic equipment. A typical grounding system connects the equipment ground wire to the metal chassis of the equipment and then to the building's grounding system. This can create a path for electrical noise to travel and potentially interfere with the operation of the electronic equipment. An isolated ground receptacle isolates the equipment ground wire from the building's grounding system. The equipment ground wire is connected directly to the grounding busbar in the electrical panel, bypassing the metal junction box and other potential sources of noise. This helps to reduce the amount of electrical noise that reaches the sensitive electronic equipment, improving its performance and reliability. When planning to install an isolated ground receptacle, ensure the electrical panel has a dedicated grounding busbar for the isolated ground circuit. This busbar should be properly connected to the building's grounding electrode system. The grounding electrode system typically consists of ground rods, metal underground water pipes, or a concrete encased electrode. Select a 12 American wire gauge or larger copper wire for the isolated ground conductor. This wire should be green or green with a yellow stripe, and it should be clearly marked as an isolated ground conductor. Run the isolated ground conductor from the isolated ground receptacle back to the dedicated grounding busbar in the electrical panel. Ensure that the isolated ground conductor is not connected to any other grounding points along the way. Install the isolated ground receptacle in a non-metallic junction box. This will help to further isolate the receptacle from electrical noise. Connect the isolated ground conductor to the isolated ground terminal on the receptacle. This terminal is typically marked with a green grounding symbol. Ensure that the receptacle is properly labeled as an isolated ground receptacle. This will help to prevent accidental connections to the receptacle in the future. After the installation is complete, test the isolated ground receptacle to ensure that it is properly grounded. Use a multimeter to measure the resistance between the isolated ground terminal and the grounding busbar in the electrical panel. The resistance should be very low, typically less than 1 ohm. Sensitive electronic equipment can be affected by various types of electrical noise, including electromagnetic interference, EMI, radio frequency interference, RFI, and ground loops. Electromagnetic interference is caused by electromagnetic fields that are generated by electrical equipment. These fields can induce currents in nearby conductors, which can then interfere with the operation of the electronic equipment. Radio frequency interference is caused by radio waves that are generated by radio transmitters. These radio waves can also induce currents in nearby conductors and interfere with the operation of the electronic equipment. Ground loops are created when there are multiple grounding paths for the same circuit. These ground loops can cause circulating currents that can interfere with the operation of the electronic equipment. Isolated ground receptacles can help to reduce the effects of electrical noise by providing a dedicated grounding path for the sensitive electronic equipment. This grounding path is isolated from the building's grounding system, which can help to reduce the amount of electrical noise that reaches the equipment. In addition to isolated ground receptacles, there are other measures that can be taken to protect sensitive electronic equipment from electrical noise. Firstly, use surge protectors to protect the equipment from voltage spikes and surges. Secondly, use power line filters to filter out electrical noise from the power line. Thirdly, use shielded cables to reduce the amount of electromagnetic interference that is radiated from the cables. Fourthly, keep the equipment away from sources of electrical noise, such as transformers and motors. Fifthly, ensure that the equipment is properly grounded. Remember that while an isolated ground receptacle can help reduce electrical noise, it may not eliminate it completely. In some cases, additional measures may be necessary to protect sensitive electronic equipment from electrical noise. Another related concept is a dedicated circuit. A dedicated circuit is an electrical circuit that is used to power only one piece of equipment. This can help to reduce the amount of electrical noise that is generated by the equipment and can also help to prevent overloads in the circuit. Dedicated circuits are often used for sensitive electronic equipment, such as computers and medical equipment. When installing a dedicated circuit, it is important to use the correct size wire and circuit breaker. The wire size should be based on the load that the equipment will draw, and the circuit breaker should be sized to protect the wire from overloads. It is also important to use a dedicated grounding conductor for the dedicated circuit. This grounding conductor should be connected to the grounding busbar in the electrical panel. If you are unsure about how to install an isolated ground receptacle or a dedicated circuit, it is best to consult with a qualified electrician. An electrician can help you to determine the best way to protect your sensitive electronic equipment from electrical noise. When working with electricity, always take the necessary safety precautions. Wear safety glasses and gloves, and turn off the power to the circuit before working on it. Never work on electrical equipment when you are wet or standing in water. If you are not comfortable working with electricity, it is best to call a qualified electrician. The NEC provides guidelines for electrical installations to ensure safety and proper functioning. Article 647 specifically addresses sensitive electronic equipment in commercial and industrial settings. While not directly applicable to residential installations, the principles of isolated grounding and dedicated circuits remain valuable for protecting sensitive electronics in any environment. The key is to minimize electrical noise and interference that can disrupt the operation of these devices. Understanding the concepts behind isolated grounding and dedicated circuits allows one to make informed decisions about how to best protect sensitive electronic equipment, even when Article 647 does not strictly apply. Consider the specific needs of the equipment and the potential sources of electrical noise in the environment when designing the electrical system. By implementing appropriate measures, such as isolated grounding, dedicated circuits, surge protection, and power line filtering, one can significantly improve the performance and reliability of sensitive electronic equipment. The purpose of grounding is to provide a low impedance path for fault current to return to the source, which allows the overcurrent protective device, such as a circuit breaker or fuse, to trip and to energize the circuit. This helps to protect people and equipment from electrical shock and fire hazards. There are two main types of grounding systems: equipment grounding and system grounding. Equipment grounding is the connection of non-current carrying metal parts of electrical equipment to ground. This includes the metal enclosures of electrical panels, equipment frames, and conduit. The purpose of equipment grounding is to provide a low impedance path for fault current to return to the source, which helps to protect people from electrical shock. System grounding is the connection of the neutral conductor of an electrical system to ground. This helps to stabilize the voltage of the system and to provide a low impedance path for fault current to return to the source. In a typical residential electrical system, the neutral conductor is grounded at the service entrance. The grounding electrode system is the means by which the electrical system is connected to the earth. The grounding electrode system typically consists of one or more ground rods, metal underground water pipes, or a concrete encased electrode. The purpose of the grounding electrode system is to provide a low impedance path for fault current to return to the source. The NEC specifies the requirements for grounding electrical systems in Article 250. This article covers topics such as the types of grounding systems that are permitted, the size of the grounding conductors, and the methods of grounding electrical equipment. Proper grounding is essential for the safe and reliable operation of electrical systems. It is important to follow the NEC requirements for grounding to ensure that electrical systems are properly grounded. Remember, working with electricity can be dangerous, and it is always best to consult with a qualified electrician if you are unsure about how to install or maintain an electrical system. They have the knowledge and experience to ensure that the work is done safely and correctly. Let's discuss conductor sizing a little more deeply. When selecting the appropriate conductor size for a circuit, several factors must be considered to ensure safety and prevent overheating. The ampacity of a conductor, which is the maximum current it can carry continuously without exceeding its temperature rating, is a crucial factor. The NEC provides tables, such as Table 310.15b16, that list the ampacities of various conductor sizes based on their insulation type and installation conditions. The ambient temperature, which is the temperature of the surrounding environment, can affect the ampacity of a conductor. Higher ambient temperatures reduce the conductor's ability to dissipate heat, lowering its ampacity. The NEC provides correction factors in Table 310.15b2 to adjust the ampacity based on ambient temperature. The number of current-carrying conductors in a raceway or cable can also affect the ampacity of each conductor. When multiple conductors are bundled together, they generate more heat, reducing their ability to dissipate heat. The NEC provides adjustment factors in Table 310.15b3 to adjust the ampacity based on the number of current-carrying conductors. Voltage drop, which is the decrease in voltage along a conductor due to its resistance, is another important consideration. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. To calculate voltage drop, you can use the following formula: voltage drop equals to X length X current X resistance /1000, where length is the length of the conductor in feet, current is the current flowing through the conductor in amps, and resistance is the resistance of the conductor in ohms per 1000 feet. In addition to these factors, other considerations may include the type of load being served, the distance between the power source and the load, and the presence of any harmonics in the electrical system. It's always best to consult the NEC and seek guidance from a qualified electrician to ensure that the appropriate conductor size is selected for a specific application. Selecting the correct conductor size is crucial for ensuring the safe and reliable operation of electrical systems. By considering factors such as ampacity, ambient temperature, number of conductors, and voltage drop, you can minimize the risk of overheating, voltage drop, and other electrical problems. Always refer to the NEC and consult with a qualified electrician for specific guidance on conductor sizing. Let's explore grounding electrode systems a little further. The grounding electrode system is a critical component of an electrical system, providing a path for fault current to return to the source and helping to protect people and equipment from electrical shock. The NEC specifies the requirements for grounding electrode systems in Article 250, Part Roman 3. The primary purpose of a grounding electrode system is to provide a low impedance connection to the earth, allowing fault current to flow back to the source and trip the overcurrent protected device, such as a circuit breaker or fuse. This helps to prevent dangerous voltage buildup on metal parts of electrical equipment, reducing the risk of electrical shock. There are several types of grounding electrodes that are permitted by the NEC. Firstly, a metal underground water pipe that is in direct contact with the air for at least 10 feet. Secondly, a ground rod that is at least 8 feet long and driven into the earth. Thirdly, a ground ring that is buried at least 30 inches deep and encircles the building or structure. Fourthly, a concrete encased electrode, often referred to as a UFA ground, that consists of at least 20 feet of bare copper conductor encased in concrete. The size of the grounding electrode conductor, which connects the grounding electrode to the electrical system, is determined by the size of the service entrance conductors. The NEC provides tables, such as Table 250.66, that list the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. In addition to the grounding electrode, a bonding jumper is used to connect the grounding electrode conductor to the metal enclosure of the electrical panel. This ensures that the metal enclosure is also grounded, providing an additional layer of protection against electrical shock. When installing a grounding electrode system, it is important to follow the NEC requirements and ensure that the connections are made properly. The connection should be tight and corrosion resistant to ensure a reliable connection to the earth. It's also important to protect the grounding electrode and grounding electrode conductor from physical damage. The grounding electrode should be located in an area where it is unlikely to be disturbed or damaged. The grounding electrode conductor should be run in a conduit or otherwise protected from physical damage. Proper installation and maintenance of a grounding electrode system is essential for the safe and reliable operation of electrical systems. By providing a low impedance path for fault current to return to the source, the grounding electrode system helps to protect people and equipment from electrical shock and fire hazards. Always refer to the NEC and consult with a qualified electrician for specific guidance on grounding electrode systems.